Alright, class. Today we're going to talk about the isentropic process, topic 7.4. So before discussing about the isentropic process, in the previous lectures we talked about the entropy change for a pure substance. We talked about the entropy change of a system that has multiple subsystem, right? And also when we saw that there is a fixed mass in the system, and entropy is of that system can be changed by two phenomena, right? So entropy of a fixed mass system can be changed by two things. One is that heat transfer, and second thing is that if the process is irreversible, right? So, and then also we saw that for a isothermal process, if the process is isothermal, then or adiabatic process, then we saw that there is no entropy change, right? So if a process of a fixed mass system is internally reversible and adiabatic, then there is no entropy change. No entropy change for internally reversible. We discussed this thing in this topic in the previous lecture, right? And if the process is internally reversible and adiabatic, right? That means that if we have a device, right? For example, in this case, it's a turbine, work producing device, and this turbine is producing certain amount of work, right, by rotating the shaft, W output, right? Anyway, so it has the input and it also has the output, okay? So steam is coming at S1 state and steam is going, or output is the S2 state, and this system is isothermal or adiabatic, right, and internally reversible, right? So that means there is no heat transfer. So if that's the case, that the system is internally reversible, and it's a adiabatic, and there is no heat transfer, then for isentropic process entropy will remain constant, right? That means there is no change in the entropy. Delta is equals to 0. So delta is equals to, we know that entropy minus final state minus entropy of the initial state equals to 0. So if there is no change in the entropy, then initial and the final entropy would be the same. So this is the isentropic process. So in words, we can write a process during which the entropy remains constant is known as isentropic process, right? So this is very important. When we do the math problem And if the problem states that the process is isentropic, that means there is no entropy change, then we have to consider this equation, right? Or this equality is that entropy of the initial state and entropy of the final states are the same. So now also in quiz, I may ask, like, when isentropic process is applicable for internally reversible or internally irreversible. Also, I may ask, like, isentropic process is applicable for adiabatic, or if the system is only adiabatic, or if it doesn't matter. So you have to be you have to consider all those conditions for isentropic processes. So next thing is that when you do the math problem, we use a lot of appendix, or we use a lot of diagram. Sometimes we use a lot of table. So what is the significance, or from where this diagram came, right? So a little bit of the background in this topic. So this topic is 7.5. 7.5 property diagrams involved in entropy. Involving entropy. So let's consider a property diagram, TS diagram, since we are talking about the entropy in this chapter. So let's have a entropy diagram, right? So if you have a process like this, so this is, let's consider this is the process state 1, and this is state 2, and this process is internally reversible process, right? And then if we consider a differential element, so by the way, this is S and this is T, right? TS diagram. If we consider a small element, differential element, what would be this element? This element would be ds, right? So let's write this one, ds. And then the area of this element, since it's a small element, we can consider this is a rectangle, right? So this area of this small element, let me write it here like this. The area of this small element is nothing but t times ds, right? So now from the previous class, we know that for internally reversible process, right, if the process is internally reversible, and we know that relationship between the entropy, temperature, and the heat transfer equals to ds equals to delta q, ds equals to delta q over t, right? We wrote it like this, internally reversible. So from this case, if we rearrange this equation, then it will be delta q internally reversible process t times ds. That means this t ds of this area, it's representing nothing but the heat transfer, right, of that system. So now what is the significant? We consider here the small area. Now if we look at the entire if we look at the entire area under the curve, right, this curve, I'm making a shadow, right? Entire area under this curve, what would it will gonna represent, or what is the meaning of this curve, right? Area under this curve. So let's take a look on this one. So that means we already have the differential area, this small area, right? So what is the representation of the entire area? So if we want to calculate the entire area under this curve or this process, then we have to take the integral from this state 1 to state 2. So let's take the integral from the state 1 to state 2. Then we will get if we take the integration in the both side, then we'll get the q internally reversible equals to integration of t ds from state 1 to from state 2, right? So, and also let me write it this way too, 1 and 2. So this is the representation of the total heat transfer when the system is undergoes from state 1 to state 2, and this is the representation of entropy change when the system is going from state 1 to state 2. So that means we can write this term, right, equals to q internally reversible or the total heat transfer during this thermodynamic process, and this will be 1 to 2 t ds, right? So now if we consider a special case, what is that special case? If we consider that when this thermodynamic process is happening, then the temperature remains constant. So if temperature remains constant, then this above expression will be internally reversible equals to T naught. Let's say consider that constant temperature is T naught. So T naught of 1 to 2 ds. So this is nothing but T naught equals to S2 minus S1, right? So that means from this or we can write in other form too. It's the same thing, T naught. Yes, that means that entropy change during a internally reversible thermal process, right? Entropy change during a internally reversible thermal process times the temperature is nothing but the total heat transfer of that system. So during this is one important, I would say, equation we need for we need it for mathematical calculation, or if we do the math problem, which eventually we'll do later of this class. We will use this equation that if the system is internally reversible, then the total heat transfer is nothing but the temperature times the entropy change. Now what if the system is isentropic, right? For isentropic process, so first of all, isentropic process, there is no entropy change, right? If there is no entropy change, that means that the process is reversible, or chances is that there is no heat transfer, right? So for the isentropic process, we know, or we can we know that TS diagram, the process 1 to 2, it will look like this. If it is a TS diagram, right, the process will gonna look like this. That means if this is the state 1 and if this is the state 2, or vice versa, right, then it's just simply a vertical line. That means there is no entropy change. The entropy at this along this line, for entropy at 1 and entropy at 2 is the same, right? So for an isentropic process, TS diagram is easily recognized by this vertical line, right? So in isentropic process, since there is no heat transfer, that means that the area under this process must be 0. However, if the system is internally reversible and there is an entropy change, then the area under this process curve is representing the total heat transfer. So it is important to know that for internally reversible cycle, what is the area under this curve, what is the representation of the area under this curve. This is nothing but the total heat transfer of that system. But if the system is isentropic, then there is no area under this curve. This is just a single line. So I think that's the important thing about the isentropic process. And for example, for instance, the internally irreversible or internally reversible process, right? So that's the thing. Another important thing we use for mathematical problem, right, mathematical problem, it's the Mollier diagram. So this is the entropy, temperature versus entropy diagram. We also use enthalpy versus entropy. Excuse me. Enthalpy versus entropy, right? Another name of this is HS diagram. HS diagram. So there is a name of this diagram, it's called Mollier diagram. Mollier diagram. So this diagram, we can find this diagram in appendix A10, right? So this diagram is basically representing the relationship between the enthalpy and entropy of a thermodynamic system. And this diagram, TS diagram, will use both of the diagram, TS diagram and HS diagram from A10 appendix for the mathematical problem. And one last thing is that students are highly encouraged to do the math problem, example problem of 7.5 and 7.6, and we'll do some math problem from the exercise. We'll do some math problem from the exercise based on the isentropic process, and also if the process is internally reversible, then what is the total heat transfer, or maybe what is the total entropy change. So we'll do this problem in the later section of this class. So I think for the moment, these two topics is covering the entropy change of an internally reversible process and adiabatic process. I think that's all for this class. Thank you.